Hey guys, here to do the problem from the lab to find the coefficient of friction on a incline. So I have so far, I just made up some numbers. Say our weight of our shoe was 2.5 newtons. The force of friction static, the average, that you should get that from your graph, right? You do 3 trials, say the average was 4 newtons, and the force of friction for kinetic. After 3 trials, we averaged together and we got 3.5 newtons. And then, of course, we have our formula for friction over here is mu times the normal force times the cosine of theta. Because, of course, if we draw a little free body diagram right here, we have the weight of the shoe going down. So it made an angle of 15 degrees. I have the part of that weight going down the ramp and into the ramp. So, I said cosine. I should have said sine, huh? Whoops. Oh, no, I'm right. It's cosine. Just kidding, it is cosine. So this component here, right, that's cosine of the angle. Here's the angle. This is also 15 degrees there. So the way the shoe, 2 components of gravity, down the ramp, into the ramp, normal force up this way. It's in. Friction's going to be back this way. Then we also have an applied force going down the ramp. I think I told you, most of y'all, I think I did, to pull the shoe down the ramp as opposed to up the ramp, but you'll see it in a minute. It doesn't really matter what you do. All kind of balances out in the end anyway. So force of friction, mu, normal time, cosine theta. Why cosine again? Because remember, this component here must match this component. They must equal each other and cancel out, because the shoe is not floating off the ramp or going into the ramp. It's sliding down the ramp this way. So this component and that component must cancel out. So this component here, let's go and do it real quick, is going to be weight of my shoe was 2.5 newtons times the cosine of 15 degrees. Make sure I'm in radians. Make sure I'm in degree mode. All right, so 2.5 cosine of 15, 2.4. So that would mean that my force of friction. Well, let's just wait on that actually. So let's just get these components done. So that component there, the normal force in equal 2.4 newtons. Jordy, hey, stop it. 2.4 newtons. All right. So Tuesday. Honestly, Jesus Christ. Okay, sorry. Anyway, can y'all just get out of here? Get out of here. Jordy, get out. Just leave. Just go outside for a minute. Good Lord. I'm trying to make a video. All right. So our normal force is 2.4 newtons. It's a little bit less than the weight of the shoe. It's not that big of an angle, right? It's close to flat, not that much of an angle. So all right, so here's our normal force. All right, we also have though the applied force. Now remember, the readings from your LabQuest device, those were actually how hard you were pulling on the device, right? So I know I labeled these as force of friction static average, force of friction kinetic average, but really what you were doing there was, that's how hard you were pulling the shoe, right? Because that's what the lab was actually measuring. So we're gonna take this number here. I'm gonna add that. That's actually the force with which we were applying, right? We're gonna add that to this component of gravity going down the ramp, and that's gonna be our total force. So if my weight of my shoe is 2.5, now I'm gonna do sine of my angle, 15 degrees. To get this component here going down the ramp, 2.5 sine 15 degrees, I get 0.65, 0.65. So that number plus the number I was using from the LabQuest, so 4 newtons plus 0.65 equals 4.65 newtons. That's actually my force of friction, right? Because we had to consider the weight of the shoe being pulled down by gravity plus my applied force. Now I go back to my formula up here. Now I know the true force of friction is 4.65 newtons. So I'm going to plug in my formula up here, 4.65 newtons equal, that's my force of friction, mu, which I'm trying to find, times the normal force. And I guess I don't need a cosine theta there anymore. I guess I should have said, well, never mind, doesn't matter. So just leave it like that. I guess the reason I wrote that originally, guys, was because I was thinking in my head force of friction equals mu times the weight cosine theta, right? If I let that as weight times cosine theta, that would give me this component, right? But if I put the in there, so that was really kind of redundant of me. Didn't need to do that. So sorry if that confused you. So here's my formula for force of friction. So I'm going to take this number now, plug that into this number, plug it into here, so I get 4.65 equals mu times normal force. Remember, I already found normal force, right? So 4.65 equals mu. Normal force, we said, was this component, which was 2.4 newtons. So I want to divide everything by 2.4. Cancel there. This will cancel and get the, so it'll be 4.65 divided by 2.4. And my mu equals 1.94. That's really high. Probably the reason why I'm getting such high numbers is because I made up my numbers. These aren't real. Sometimes when you make up funky numbers just to do a problem real quick, you end up getting answers that kind of don't make sense. It's possible to have a mu this high, but it'd be really weird. It'd be like really sticky. Like when Tuesday is hanging. Oh, she looks evil. Hanging from my, crawling up a tree or whatever. She probably looks, might have a mu that high, but with her claws. But normal every day is just pretty high. But it's not the point. The point was to show you how to do it. Let me recap real quick because I know that was a little confusing because I'm a little rusty, I guess. So we said the weight of the shoe is that, force of friction from the LabQuest device for static friction was that, and kinetic friction was this. Again, from the LabQuest. But then we have to consider the fact that we're on a ramp, right? So there's the shoe. Let me get a little closer. Okay, so there's the shoe, right? On an incline, so we have part of the forces going down the ramp are the weight of the shoe, right? That component of its weight, plus my applied force. All right, I found this component here using the weight of the shoe times the cosine of 15 degrees to find the component here, which must equal this component. They must cancel out. So this component is normal force. Found that to be 2.4. Then I had to find this component and add that, this component I'm pointing at now, this component, add that to the force from the LabQuest device, because that's how hard I was pulling on the shoe. So it pulled on it that hard, plus I had gravity helping me go down the ramp, right? So those two things, that component down the ramp, plus this force from the LabQuest device, I get 4.65 newtons. That's the force down the ramp, right? That's the actual force I'm applying. Take that number, plug it in my equation for mu here. Force of friction equals normal force times mu divided by n, and I get 1.94. All right, so when we do stuff on inclines, we have to consider all the force going down the ramp. So when you pull that LabQuest down the ramp, right, the LabQuest is just measuring how hard you pull the shoe. But we also have to consider the fact that gravity is also pulling the shoe down the ramp, and all those things are overcoming the force of friction going back in the way. So what about for kinetic? We do the exact same thing for kinetic, except that instead of plugging in a 4, adding it in here, we would add in the 3.5 instead of the 4, and we'll get a slightly lower mu. It'll slightly lower number. All right, so I hope that helped. I know a little confusing. I'm a little rusty. It's been a while, and things are happening. So I hope that was useful to you and helpful. If not, message me on Remind. I'll help you out. You have a great day, and I'll see you all tomorrow.